exponential functions and their derivatives. We'll start with a brief review of exponential functions, and then we'll go on and talk about the calculus of them. So first, recall that an exponential function is a function of the form f of x equals a to the x, where, for our purposes, a is a positive constant. And so recall that if we want to graph this function, well, if a is between 0 and 1, say, for example, if we had the function 1/2 to the x, recall that this is a decreasing function. It has a vertical intercept at 0, and we get a graph that does something like this. So recall that the domain then would be -infinity to infinity. The range is 0 to infinity. The limit as x approaches -infinity. So as we go further to the left, as we let x approach very large negative numbers, this limit approaches positive infinity. And if we let x approach positive infinity, as we move further to the right, recall that the graph it becomes asymptotic and approaches 0. All right, so that's if we have a between 0 and 1. Now, if a is greater than 1, so say, for example, we had the function 2 to the x, then we get an increasing curve, an increasing function. Now again, the domain is -infinity to infinity, and the range is still 0 to infinity. And our graph might look something like this. It passes through 0, 1, and then increases. And the limit as x approaches -infinity is now 0, and as x approaches positive infinity is infinity. Okay, so you should still be able to sort of remember these sketches from what you learned in algebra, and we're gonna use some of these ideas for especially those limits later on in this course. So make sure that you remember those limits. Exponential functions have various properties which are important to remember. Recall that if we have a base to a sum, a to the x plus y, that we can write that as a to the x times a to the y. You might have learned this as a quote-unquote product rule for exponents. Similarly, a to the x minus y is a to the x divided by a to the y. A to the x to the y is a to the x times y. And the product ab raised to the x power is a to the x b to the x. We might need to use one or two of those properties later on. All right, so now let's start looking at the calculus of exponential functions, and we'll start by calculating d by dx of e to the x. So what's the derivative of this function? Well, if we use the limit definition of the derivative, if I call f of x e to the x, all right, then d by dx of e to the x would be would be the limit as h approaches 0 of f of x plus h minus f of x over h. And so that would be the limit as h approaches 0 of e to the x plus h minus e to the x over h. The limit definition of the derivative, something we saw in Calculus 1. All right, continuing. So this would be the limit as h approaches 0. Now this e to the x plus h, I can break that apart as e to the x times e to the h. Still subtracting e to the x, and still divided by h. Now I'll use a little bit of factoring. I can factor out the e to the x, and I'd have e to the h subtract 1 over h. Now, since my limit is in terms of h, and I have this e to the x is not dependent on h. So I'm allowed to bring that outside the limit. And so this becomes e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Now, we cannot simplify this limit using algebraic techniques. But we could, if we used a calculator and let h approach 0, we can show that this limit approaches 1. That limit approaches 1, and so what we've just shown is that this whole thing, e to the x times that limit, is e to the x. So what have we shown? D by dx of e to the x is equal to e to the x. The derivative of e to the x is e to the x. So this is a very interesting function. Its derivative is itself. All right, so again, d by dx of e to the x is e to the x. Now, if we need to calculate the derivative of some composite function, e to the f of x, we apply the chain rule. So the derivative of e to the f of x would be e to the f of x times, by the chain rule, d by dx of f of x. And all of our old rules still apply. Product, quotient, all those old rules we can still use. So here's an example. We're asked to differentiate the function g of x is the square root of x times e to the x. I'm going to apply the product rule here for differentiation. So recall that I tend to think of it like this, that if I want the derivative of f times g, that's f g prime plus f prime g. I'm going to think of the square root of x as x to the 1/2. So I have x to the 1/2 times e to the x. That's my original function. So then g prime of x would be f g prime, x to the 1/2 times e to the x. The derivative of e to the x is e to the x. All right, so, and then plus f prime. The derivative of the square root of x, that would be 1/2 x to the negative 1/2 times g, e to the x. All right, now I'm going to do a little bit of factoring here to clean this up. I can write g prime of x, I can factor out the e to the x, and I'm going to write these other factors back in terms of the square roots. So x to the 1/2 is the square root of x, plus 1/2 x to the negative 1/2 is 1 over 2 times the square root of x. And so there's the derivative of g of x. All right, here's another example. We have y is equal to e to the x over 1 plus x. So here I'm going to use the quotient rule to differentiate this function. All right, so then y prime would be low d high. The derivative of e to the x is e to the x. Minus high, the high function is e to the x. D low, the derivative of 1 plus x would just be 1. And then in the denominator, we would have 1 plus x squared. All right, now I'm going to use a little bit of factoring here. Y prime would be equal to, in the numerator, both of the terms have an e to the x. So I can factor out e to the x, and I'd have e to the x times 1 plus x minus 1. The denominator is 1 plus x squared. And so I'd have, let's see, 1 plus x minus 1 is x. And so I would write this as y prime equals, I'll write it as x e to the x over 1 plus x squared. And we are also asked to differentiate y equals cosine of e to the pi x. All right, so let's see. We've got to be careful here. I've got a composite function, and I have e to the pi x is inside the cosine function. All right, so then y prime would be the derivative of cosine, so negative sine times the inside quantity times, negative sine of the inside quantity times the derivative of the inside quantity. So now the chain. Y prime would be negative sine of e to the pi x. Now the derivative of e to the pi x, that would be e to the pi x times the derivative of pi x. So again, the chain. Now the derivative with respect to x of pi x would just be pi. So I'm going to write this as y prime would equal negative pi sine of e to the pi x times e to the pi x. So there we had to use the chain rule a couple of different times. All right, an application. Find the equation of the tangent line to y equals e to the x over x at 1e. All right, so I have a point. If I want the equation of the tangent line, I need the slope at that point. So to find the slope, I'm going to calculate the derivative. If y equals e to the x over x, then y prime would be, let's see, quotient rule, low d high. The derivative of e to the x is e to the x, minus high, that's e to the x, d low, the derivative of x is 1, over low squares, so that would be x squared. So I've got x e to the x minus e to the x times 1. I could write that as e to the x times x minus 1 over x squared. All right, so there's the derivative of the function. Now, calculating the derivative at 1. That would be e to the 1 over 1 minus 1 over 1 squared. And so that's e to the 1 times 0 over 1. That's 0. So the slope is 0. And so then we would have y minus e is equal to 0 by x minus 1. And so notice that wipes out the right-hand side, and we can just write this as y equals e. So it turns out to be a horizontal line. Y equals e. Find dy dx if x e to the y plus y e to the x equals 1. All right, so this is, here we have this equation. It's not a function, right? This is not a function. We don't have y equals. And in fact, it would be very difficult, actually it's impossible, I think, to solve for y in this equation. So instead what we've learned to use is that technique called implicit differentiation. So what we do is we apply the differential, d by dx, to the left-hand side of the equation and to the right-hand side of the equation. Now the right-hand side is easy. D by dx of 1 is 0. On the left-hand side, we have to be very careful here. We have to apply a few different rules. So let's see. I'll have d by dx of x e to the y plus d by dx of y e to the x. And so I just, the sum. Now, each of these is a product, right? I have x e to the y and y e to the x. Each of those is a product, so I'm going to use the product rule. All right, so d by dx of x e to the y. Well, that would be x times d by dx of e to the y plus d by dx of x times e to the y. Plus, so that's from the first term. Now I'll go ahead and, here's the second term. D by dx of y e to the x. That would be y times d by dx of e to the x plus d by dx of y times e to the x. And that's still equal to 0. All right, so that's the product rule. Now let's see. D by dx of e to the y. The derivative of e to the y, well, that would be x times e to the y. The derivative of e to the something is e to the something, and then dy dx, the derivative of y with respect to x, plus d by dx of x, the derivative with respect to x of x is 1 times e to the y, plus y times d by dx of e to the x. The derivative with respect to x of e to the x is just e to the x. Plus d by dx of y, that's dy dx, times e to the x is 0. Alright, so now what we do is we group everything that has a dy by dx together. So let's see, I have dy dx times x e to the y plus dy dx times e to the x. Everything that's got a dy dx is on the left-hand side. I'm going to move everything that doesn't have a dy dx onto the other side. So let's see, I've got a negative e to the y and a negative y e to the x. Now notice that the left-hand side I can factor as dy dx by x e to the y plus e to the x. And so then dividing through, and so that then is equal to negative e to the y minus y e to the x. So now I can isolate dy dx for division, and dy dx would be negative e to the y minus y e to the x over x e to the y plus e to the x. And so there's dy dx through implicit differentiation. Another application. Find the absolute minimum value of the function y equals e to the x over x for x is greater than 0. Earlier, we calculated the derivative of this function as e to the x by x minus 1 over x squared. And from here, we would note, well, first, x cannot equal 0. And notice that's okay because we were only concerned about values of x greater than 0. I mentioned that note because we have the denominator of x squared, and so the denominator cannot equal 0. So now, recall from Calculus 1, once we calculated the derivative, we wanted to find where it was equal to 0 to determine any minimum or maximum values. So we would now solve y prime equals 0. So where is e to the x by x minus 1 over x squared equal to 0? Well, that can only equal to 0 if the numerator is equal to 0. E to the x by x minus 1. Now, e to the x can never equal 0. E to the x can never equal 0. Remember, it's asymptotic, but never equal to 0. And x minus 1 can equal 0 if x equals 1. So we have a critical value at x equals 1. And then we learn to maybe set up a little chart. And so I'll set up my partial number line. All right, so here's 0. We're only concerned about values that are greater than 0, and I'll place 1, my critical number, on the number line, and I'll test values into the derivative. So the derivative, all right, testing in y prime, So I'll test a value, how about 1/2, or some other number between 0 and 1, and how about 2? Test a value on each interval, and notice that y prime of 1/2, well, let's see, e to the 1/2 would be a positive number. 1/2 minus 1 would be a negative number, and 1/2 squared would be a positive number. So I have a positive times a negative, which is a negative over a positive. This is a negative number. And if I test y prime of 2, e to the second is a positive number, 2 minus 1 is a positive number, and 2 squared is a positive number, so therefore positive. So what that tells us, remember, is that the original function was decreasing and then increasing. And so I would expect a minimum value. And since this function, since we're only looking at x is greater than 0, that must be the absolute minimum of the function must occur when x is 1. So let's see, f of 1 would be e to the 1 over 1, which is e. And so then f, I should have used y instead of f. All right, so y of 1 is e to the 1 over 1, which is e. And so then y has a minimum value of e at x equals 1. Since the derivative of e to the x is e to the x, it seems reasonable that we should be able to integrate using the same idea. And so the antiderivative of e to the x is e to the x plus a constant from integration. So let's look at some examples where let's look at some integrations. So here we're asked to evaluate, we should have a dx here. Sorry about that. Evaluate the antiderivative of e to the x sine e to the x dx. All right, so this is not a simple integration. It's not just e to the x. We have e to the x sine e to the x. So here I'm going to use a substitution. So remember that one thing to try in substitution is, sort of whatever's inside the function, whatever's inside the quantity. So I'm going to try letting u equal e to the x. If I let u equal e to the x, then du would be e to the x dx. And I see that I have an e to the x dx. So this integral can be rewritten as the integral of sine u du. And that's a simple integral. Sine, the antiderivative of sine is negative cosine. So this becomes then negative cosine u plus a constant. Let's put this back in terms of x. So negative cosine of e to the x plus a constant. And of course, since this is an indefinite integral, we could check this through differentiation. All right, here's another example. We're asked to evaluate the integral of e to the 1 over x squared dx. All right, again, this doesn't look simple. I'm going to try a substitution. What if I try u equals 1 over x? Well, recall that that's the same as x to the negative first. And so then du would be negative 1 x to the negative second dx. And I can write that as negative 1 over x squared dx. And so I see I've got this over x squared, so I would just need to maybe rewrite this a little bit. I would need a negative, and there's the 1. I can always put in a 1. But now I've put in that negative on the inside, so I need another negative to balance it. I'm going to put that other negative outside. And so I've got negative 1 over x squared dx and e to the 1 over x. So I can rewrite this then as negative integral e to the u du. Right? Because the 1 over x, that was my u, and I multiplied by a negative 1 on the inside and outside to balance, but that gave me the du that I needed. All right, so then the integral of e to the u du, that's e to the u plus a constant, and so then negative e to the 1 over x plus the constant. All right, how about a definite integral? So here we're asked to evaluate the integral from 0 to 1 of x e to the negative x squared dx. Again, this seems like a good place for a substitution, so I'm going to try u equals the exponent. All right, so I'm going to try u equals negative x squared, then du would equal negative 2x dx. I have the x, so I would need a negative 2 multiplied in, and so I would need a negative 1/2 on the outside to balance that. Now, if u equals negative x squared, if x equals 0, u equals 0, and if x equals 1, u would equal negative 1. So I can write this in terms of u. This would be negative 1/2 integral u equals 0 to u equals negative 1 e to the u du. Now notice I have this integral from u equals 0 to u equals negative 1. We usually don't like that. We want when we want the limits of integration, we like them from the lesser number to the greater number. And we can remember, we're allowed to flip this integral. We're allowed to flip the limits of integration. And to do that, we have to also throw in an additional negative. So I have negative 1/2. Now I'm going to flip the limits of integration. So I'm going to bring in another negative 1, and I'm going to rewrite the integral from u equals negative 1 to u equals 0. E to the u du. All right, so now I have negative times a negative. That's a positive 1/2. The antiderivative of e to the u is e to the u. Since this is a definite integral, we don't worry about the constant, and this is from negative 1 to 0. And so this becomes 1/2 e to the 0 minus e to the negative 1. Now e to the 0 is 1, and e to the negative 1 I'll write as 1 over e, so I can write this as 1/2 of 1 minus 1 over e. And that's an entirely acceptable form. All right, that concludes this section.